So today I will talk about sparsity for control. So if you notice, I put a question mark here because I don't have any solid theory saying that sparsity is really helpful for control, but I do have some intuitions. So today I just try to convince you that sparsity might help. So first, what's sparse representation? So when we talk about sparse representation, we usually mean a representation in which many components are zero. But actually, there are two different sparsity definitions. One is lifetime sparsity, which means each component in the representation is sparsely active across time, across different samples. So each feature only responds to a small subset of your input space, a local region of your input space. And another one is instance sparsity, which means each instance or each sample has a sparse representation. So for any input from the input space, we have a sparse representation for that input. Okay. So one example is tile coding. So I assume everyone knows what's tile coding and how it works. So tile coding has lifetime sparsity because each feature in tile coding representation only responds to a small tile. Like the green feature only responds to this green tile. And for other inputs outside the tile, the feature will just be zero. So it's sparsely active across the input space. And it also has instance sparsity because for each state, the tile coding representation has at most number of tilings active features. So that's one example of the sparse representation. But what about sparsity in neural nets? So when we say sparse neural nets or sparse representation in neural nets, there are usually two different meanings. One is dense activations and sparse weights, which is the figure on the left. Another one is sparse activation but dense weights, which is the figure on the right. So in this talk, if I say sparse representation or sparse neural nets, I mean these sparse activation neural nets, just to clarification.
Am I supposed to imagine on the left-hand side there's less arrows?
You mean arrows for
less
prediction?
Connections?
Oh yeah, this connection is sparse. Some of them are zero.
Some of them are missing.
And this one is the activation are zeros. So the motivation is when we run control experiments with neural network as functional approximation, we usually see is quite unstable. So sometimes you see the agent learns an optimal policy, but it fails in the next episode, and it learns the optimal policy again and it fails again. So I did a very simple experiment here. So assume we are given sparse and dense representation from a neural net. So I want to see how well they do in these classic domains. Right. So in general, the blue lines here are the sparse representation with the same control algorithm, epsilon greedy salsa. So in general, sparse representation did much better than dense representation. And each lighter line here represents the run. So for example, in Acrobat, you can see the blue light lines are kind of close to each other, but the red line has huge variance. So it's very unstable. Okay, Adam.
Down here it says train the neural network first. Can you explain the training scenario here that produces the setup?
Also, I train a neural net given the set of data using mean squared TD error. So one is I train the dense neural nets, another one is I train the sparse neural nets. And then I fix these two neural nets. I just use them to generate representation for the control experiment.
So for the control learning, you just adapt the output layer?
Yeah.
What are these numbers in parentheses?
Oh, that's a good question. That's the learning rate for salsa. Yeah.
So you have all these tasks. Does it mean that you're solving all these tasks in an online manner, or are you doing experience replay?
Oh, no, I use a batch of data to learn neural nets. And then I just learn learn to do control incrementally using *0, just *0. So here.
What do you mean by use a batch to learn the neural network?
So I predefine a BFA policy and gather some data, and I use the data to train our neural nets.
What is the objective?
Mean square TD error.
So what's the difference between the sparse network and the use dropout for the dense network?
Yeah, I will compare sparse network to dropout in the next experiment.
How do you get this sparse network?
Yeah, that's a good
why
question.
not do them, better?
I will answer this question in like a few slides. Thanks. So here,
Why
yeah.
not do them together? The two steps.
I mean, why do you learn representation first? And
I mean, why not do them together? Why not do together? Like, tuning the neural network, get a feature.
because one question is we don't know how to learn sparse neural nets incrementally. So I just tried here. I just want to show we have sparse representation, we have dense representation. How different that acts if we're doing control.
What is representation? So you have some features, and using that you have a linear value function?
Yeah. So I learned the weights. So given the input, I use this layer as representation. Right.
Sorry to ask you so many questions about the pre-learning step, but to train the networks, did you do like a fixed amount of gradient descent steps, or was it until you reached a certain error threshold? Like when did you stop the training of these two networks?
I fixed the number of air paths.
Okay.
Right. Right. So here I just want to show you, given different representation, you can see the performance differs a lot. So what might be a problem with neural nets in control? So one issue is catastrophic forgetting problem. So if we have dense activations in our neural nets, you can imagine each update change the value function, your estimate value globally for all of your states. So assume we have an agent doing many iteration of updates in one state, it might eventually overwrite what the agent has done in other states. So that's the forgetting problem. And why sparsity helps to solve this problem? One is, my intuition is sparse representation is more robust to forgetting problem, since each feature only responds to a local region of your input space, or only responds to your local dynamics. So when you do an update, you only change the value functions for that local region. Yeah, so I think it might be better to have visualization. So I plot the activation map of each hidden neuron. So one small grid square here is the activation map for one hidden unit. So this is the map for first hidden unit, this is the map for second unit, the map for third unit, and so on and so forth. And one point in this square corresponds to one point in the power word domain. So this point here is the state in this power word domain. So one square corresponds to the whole power word domain. And the color of the point corresponds to the activation magnitude here. So you see the blue points correspond to 0 magnitude for the first hidden unit, and this green point corresponds to around 0.6 magnitude because it's yellow in this state in power word. So do you have any question in this?
What is the gate function that you're using? Are you using ReLU gates or?
What do you mean gate?
The activation function that you're using.
Oh, the activation? Yeah, I used rectifier linear unit.
So is this supposed to benefit from lifetime sparsity?
Yeah, right. So how do we train our neural nets? We actually doing this, we enforce lifetime sparsity, which I will talk about in the next slide. Yeah. And so you can see for the sparse neural nets, each hidden unit only responds to a small local region in the whole input space. But on the other hand, if we have dense neural nets, each hidden unit, like this one, responds to all the input space. So you can imagine if you have the agent doing update in this state, it will also change the Q value or value function for these states. But when you see these two states in the power word, they shouldn't be grouped together. So that's one of the problems of dense representation. Right. Okay. So let's go back to the second point. I think sparse representation will provide sample efficiency in incremental learning, which means we can set the step size more aggressively. So that's correspond to Nico's question. So you can see the learning rate here for all domains. I can set the learning rate for sparse representation much higher than dense representation. So it converges faster than dense. So that's another point I think might benefit from sparse representation. Okay. So I'll assume like you think sparsity might help in control. So the second question is, how can we learn sparse neural nets? So I will just briefly introduce a simple method we used, but I won't go into the details. So we model each activation of the neural nets, yj, as a random variable, and we try to match the random variable to a set of distribution. And the distribution should have high density at 0 or at small values. Here is the PDF. So our optimization problem will be, we optimize the state of data, which is our original objective function for training neural nets, but we constrain on the P of yj and the set of distribution Q. So here we just try to enforce lifetime sparsity. So this constraint is independent for different hidden units. But the first optimization question is too difficult to solve. So instead we optimize the Lagrangian given some distance measure. So that will be this second equation. We minimize the original objective function plus the Lagrange multiplier of some distance. So we can view the second term as a regularization term. And for some spatial DQP, we can have a closed point expression for the second regularization term, which is the equation here. And so we have two hyperparameters, lambda and beta. Beta j is the mean activation for yj. So now we have a sparse regularization method for neural nets, but if it outperforms dense neural nets, we are not clear if the benefits from the regularization part or benefits from it provides a sparse representation. So in this experiments, we compare our sparse regularization to other popular regularization in neural nets, L1, L2, and dropout. And the experiment setting is the same as the previous one. We collect a batch of data, we train neural nets using mid-square TD error, and then we fix the neural nets. We perform epsilon greatest outside 0 with constant epsilon equal to 0.1. So this is the result. So first of all, I am still running the experiment for capture, so there's no result here. And we can see in general, the blue lines are sparse neural nets, and it kind of did very well in all of the classic domains. And for L1 and L2, it did pretty well in mountain car also. But for power word, I think it did quite okay. If you remember the dense neural nets for power word, it didn't learn anything. So I'm kind of surprising, just simply shrinking the weights, you can make the neural net work in power word. And then dropout performed really bad. I think one of the reasons might be because we are using a shallow neural nets, only 2 layers. And people use dropout usually for training like super deep neural nets to faster the training to prevent overfitting. But since we are using shallow nets, it's not helpful. Yeah. So I hope these results will convince you. Yeah.
How many runs is this?
It's 10 runs. I did 10 runs. And this is the, I think, 95% confidence interval. So I hope these results will convince you like sparsity kind of useful in control, better than L2 norm. Yeah. So my conclusion is sparsity might be helpful in control if you are using neural nets because it provides local features. Another point is dropout and other regularization methods. They regularize neural nets to better generalization to prevent overfitting. But I think the sparse regularization is force neural nets to pick another equally good but more useful solution for control. Right. So that's it.
I have questions, actually. On the results you have, those 10 runs you said, and so, but here there's a pretty regular pattern in Puddle World across 10 runs. I'm not sure my question is. I'm just surprised.
I mean, like when you pick, it's
yeah,
over
like it
pick.
goes up.
Because I fixed the, wait, I think that's, I think maybe they are not at like exact value.
Sorry, what do you mean? They're not.
They just have peak because sometimes it didn't do well. It has 1,000 steps per episode, so the average will be much higher. So maybe one of these one is 1,000 in this step, so the mean is super high.
Sorry, I don't know if I missed it. For this experiment, did you train everything online?
Oh no, it's the same.
Oh, it's the same.
I train neural nets.
Before? Oh,
Yeah.
okay.
I still don't understand that training scheme. Why do you have this? So okay, for sparsity, you might need a two-phase training process.
Yep.
But maybe you should have also compared with where you're not using a sparsity, you just train it in one go, like end to end with experience replay, for example.
Oh, you mean? So I don't pre-train the neural nets. I train the neural nets incrementally, but I use the like experience buffer.
Yeah, I don't understand that part. What is that part?
Because one problem is, if you see here, we need a beta height j, which is the mean activation for yj. So if you want to estimate this, you need to have a batch of data. Of course, we can use mini batch to estimate.
Okay, so this is for sparsity.
Yeah.
But for dense network, why do you have this two?
Because it's more fair.
Comparison? Okay.
If we run sparse neural nets like two stage, we should also compare neural nets with 2 stage. It's like more fair comparison. And actually, pre-training the neural nets like will provide some benefits. So if you train L2 neural nets online, I don't think you can learn anything in the first episode, which is 1,000 always.
Okay.
Can you please go back to the slide where you had the feature maps? Yeah. So you said that you're using rectified linear units. I'm not. I think rectified linear units are supposed to have a linear response to the input space.
Yeah. If we use one,
They should not be able to respond to disjoint parts of the state space.
you mean like this one?
Yeah, that's not linear, and the one below it to the left is responding to.
Oh, you mean this one?
Yeah, to disjoint parts of the input space.
Yeah, I think that's a good question.
Possible for reducing.
Yeah, I'm not sure how can you get this actually.
So Vincent did mention he has 2 layers. The first layer can do whatever it wants, and the
Oh, yeah.
second layer is made sparse. So the first layer can learn whatever cross products it would like to learn, and then the second layer is sparse.
All right, yeah, it's 2 layers.
Yeah, there's
2 layers, yeah. One hidden unit, one hidden layer, 2 layers. Well, I should say 2 hidden layers and 1 output layer, which is the value. Step value.
Sorry, I think you mentioned this, but I couldn't quite hear. Did you say that you stopped every episode after 1,000 times? Like, do you have a max episode length? Because your X
Oh,
values on your graphs are...
yeah, this, let me see. For these 3 domain, the max step size is 1,000. For catcher is 100,000.
Can you go back to the heat maps? So can you interpret these that neurons which are firing at some local region, they share some common property over here?
That is to fire in the same region.
Yeah, so if you superimpose this on your domain, so the region where the neuron is firing, do they share some property or something? I mean, can you interpret them?
You mean, why do they fire in the same local region?
Yeah. Can you interpret them?
No, I
no.
cannot. But we also try, because we've seen this many times, we kind of decrease our instance sparsity. Well, I should mention, using our lifetime, just using the sparse regularization will also encourage some instance sparsity. But when you have like these 2 hidden neurons here, each state here will activate the 2 things which are highly correlated. So I also try to kind of enforce the learning independent features, but it doesn't seem working well. So you can think of just one is redundant and one is not redundant. Maybe because the initialization waits, so make these 2 hidden units learn the same thing.
I can go back to them. Oh, but those are questions. I
Yeah.
Then do that first.
So you explain your sparse regularization as something that enforces sparsity, but your weights in the heat map axis are much smaller than the sparse neuron net than the dense neuron. So the sparse neuron net goes from 0 to 0.6.
Right. Oh, you mean the activation manager?
Yeah, goes from 0 to 1. So is there something in your regularization that...
Yeah, that's true. You can here, if you see this equation, it will penalize everything below your hyperparameter beta.
Okay, so I can bring up my point now? Okay, I was going to answer Mana's question a little bit about this training regime, because I think lots of people would have this concern. You know, you train a representation first, and then you use that representation. But if you think about the alternative is you take a dense neural network and you let it train. Okay, and then what happens when you do that with SARSA? It doesn't work. So then you go and do all the things that DQN did. You add a target network, you add experience replay, you fiddle with all the parameters, and then you get it to work. But that sort of wasn't the point. So in some ways the point was it's not working very well in an online way. So the idea here I think was to say, let's see what happens if we train a representation offline from the same domain, like it's gathered data from all over the domain. It should be able to learn some kind of reasonable representation, and then it should be able to take that representation and actually learn incrementally. And the sparse one's actually able to do it, even though it doesn't get to adjust the representation, but you can't with the dense one. So I think there's something interesting there, but there is some issues with the fact that you don't get to adjust the representation for the policy that you learn as you go along. It's based on some other policy.
Right.
Can you also elaborate how you learn the representation? I'm still confused on that part. How do you learn the representation? What do you mean by collecting some data and doing something?
Oh.
What is that thing?
Go ahead, Vincent.
So I just define a BF policy for example, in modern car. So you collect many data, and then you do. I remember you just sample a mini batch using mean squared TDL as your objective function.
Okay, so you learn a value function.
This is mean squared TDL. You just minimize this.
Okay, so you learn a value function offline, and then you go online, and then there are these instances coming in, and then you're fine-tuning your value function.
Fine-tuning the last layer,
Only the last
the value function parameter.
Well, the last layer is not initialized to the policy value.
Oh yeah, it's just initialized to 0.
Because the data is from some other value. We're trying to learn the optimal values.
Yeah. Okay.
Yeah. How about make it? Oh, sorry.
Have you tried training the last layer with Monte Carlo updates to see like if that representation like gives a better family of functions that will be closer to the like Monte Carlo point?
I remember I tried using mean square return error to train the neural nets. I think the performance is slightly better.
What?
It's slightly better
Which one?
using mean square return error.
Oh no, I mean like so you do
Increment. You mean the incremental update part?
so you don't I mean you use the star shell for the last layer to do control, right?
Right.
No, I mean in that step, could you do that with the Monte Carlo updates? Because so there is this like factor that what kind of functions you can like have with that representation and a linear function on it. And there's also like this problem that where the t-defix point is gonna be. If you have Monte Carlo updates, you can rule out the second factor and just see what kind of functions, like what family of functions you can have with like your sparse representation or dense representation. Just wanted to see if like your sparse representation gives you a better family of functions.
Yeah, I agree. But yeah, I haven't tried using Monte Carlo, but that's a good point.
To your point, Hassan, that's a good point. In some ways, the point here was that the sparse representation is just going to be a more restricted function class. So in some ways, it can't do better than the dense one in terms of representing the true value function, but it can do better in terms of incremental learning.
Yeah. Yeah. So here, the point.
If you think of representation learning, what do? We take our narrow network class and then we make it harder to train our functions. Like we restrict the class of possible functions. That shouldn't be better in a sense, unless you have some reason that you think it could be better, like learning incrementally or something.
Yeah, my understanding is you are using some policy, got some data on train the network, and then train the control. So how about make it iterative? You have some policy and then better policy, and then train the network again and do this maybe several times.
Yeah, maybe I can try this. Thanks.
Yeah, so you said you were minimizing MSTE. So are you doing something like off policy?
I'll just. So if you like have a mean square TD error here, I just directly minimize it without any modification.
But you collect the data according to some other policy.
Yeah, but the point is I just want to train a neural net which learns some good representation for the input space. I'm not using the value function to do anything. I'm just using the representation part.
Yeah, but that is for policy evaluation, right?
Right. So the representation is learned on some policy, and I use the representation to do another policy. That's should I call it off policy? I'm not sure. But I didn't use the value function for control. I just initialize to 0 again and doing salsa. So I don't know if that would still be off policy. Oh yeah.
How would something like this scale to like Atari, for example? Because like if there's a more rigid partitioning of features, and then like in bigger domains, there's more you encounter things that you've never seen before. So how would this work in such domains?
So one thing we can do is we keep a buffer. I mean, each time we sample buffer to train this objective function. So we can learn this incrementally. But then you have to estimate beta j with mini batch, which is unbiased, which is biased. But yeah, you can keep a buffer, and each time you sample your data from the buffer, training this using this objective function, training your neural nets. I think it might work.
I think what Taher's probably asking also is, how do you deal with images? Is that maybe what you're thinking? Do you have big
high dimensional inputs?
My question is like if you have like a large domain, like the initial data that you learn features on, and then like later on, like it could be in a different space. So like how do you deal with that?
I'm gonna have to answer this one for Vincent since I've kind of forced him into this training regime. There's the point of this is not really to say we should train our representations first and then use them second. The point is just to show, look, a sparse representation can help us learn, but it's definitely not the regime we should be using. We should be training our sparse representations at the same time as learning. We're just not doing it yet.
Yep.
So you want to make the comparison as clear as possible.
Yeah, exactly. We want to remove as many factors as possible.
I know
Style
that.
coding.
Sorry, I also have my hand.
That's
So-
the worst in the front row.
I'm just trying to tease apart in my head, like maybe why the results are so bad for the other algorithms on Hello World. So I guess I'm wondering about this training regime is actually quite interesting. Do you have any recollection, or can you tell me? You said you trained it for a fixed number of epochs. Did all the networks sort of bottom out on their error at that point, or maybe the dense network takes more training epochs and it just never got to where it needed to be?
Actually, it's kind of the opposite. The sparse neural nets require more epochs to train.
Okay,
So dense neural nets converge pretty soon.
cool.
So I kind of need to like tune the learning rate so that you won't get overfitting for dense neural nets.
Okay, so that's interesting. So then the second thing is, I'm wondering what the impact is of you cutting off the episodes after 1,000 steps. So if the algorithms that are doing poorly, if they just never got to the goal in the first few, like maybe if they'd run for 1,500 steps, they would have found the goal and they would have had something useful to back up. So that might be something that, this cutoff thing can actually have a really big impact on
Yeah, I
learning.
agree.
Definitely. For all of our experiments in these domains, because we use these domains all the time, a 1,000-step cutoff seems to be enough time for them all to reach the goal multiple times. But I'm going to get Nico and Russian here if they're in this room. They would know. Nico, how soon do you cut yours off? You don't? I think Russian cuts hers off later than 1,000.
I've tried both versions, and it didn't seem to make a difference in the algorithms that I was
Yeah, that's a good point, Brian. That could be a totally impacting thing.
Like
so maybe we should increase
you
that
could
cutoff.
report it, cut to it, like you could truncate the scores that you're reporting, so
Yeah,
the
yeah.
graphs are a little bit comparable, but you could let it keep running for
Yeah, I agree. That
Right.
was too aggressive.
That's it.
In these domains, style coding would be the sort of upper bound on the sort of representation you can get to
Yeah.
get a good policy. So did you compare it with?
Yeah, it's pretty much the same as the boom line, but like smooth. So
It's
like
pretty much the
Echo
same
is
as
like
sparse?
is bar in converge
Right.
in modern car around 150.
Acrobat
Power board, I think tile coding is slightly better. I think it can be like 17 or something.
Does the initial value function for all of these neural networks going to look the same when you do your final sort of testing?
What do you mean final testing stuff?
So you do the pre-training step and then you learn and generate these graphs, right?
Yeah.
So the initial value function for all of these different approaches, do they kind of come out the same from the pre-training step, or are they maybe different?
The initialization for the value function?
So yeah, so when your agent finally, it's time to learn, and this is what we're measuring it on, and that's what's going to generate these graphs. I'm wondering what their sort of what their initial value function is there is going to depend. It's going to control how they end up exploring space early on, which is going to have a long-term impact.
But after we train the neural nets, I initialize the value function to like
But you could check what their
Gaussian.
performance was, and you could have that visualized on here to see how good they do just starting off before you then switch to your second phase of training.
No, that's not exactly what I meant. Like, so how do you initialize the value function before the second phase? Because it's a neural.
I use like Gaussian with zero mean Gaussian with variance 0.001. So it's kind of optimistic initialization because the rewards in these domains are all negative.
And I guess it's a rectified linear neural network, so they're all positive values.
Yeah, yeah. So the representation is always positive, and you have close zero initialization down here.
So I don't know if you mentioned this. There's no experience replay and no target network, right? In this?
No, just zero, incremental 0.
I think we're out of time.
Yeah.